Okay, yeah. So exam a week from this Monday, it'll be taken on Canvas, right? Through the quiz function. It'll be 60-minute exam unless you have DSPS accommodations, in which case the exam time will be lengthening to accommodate that. I was saying the things you can use are the periodic table I sent you, the sheet of constants that I sent you, your calculator, a pencil, plus a one-page sheet, all right? So you can have one page of things you write down whatever you want. You can use that on the exam as well, all right? In addition, there's a pre-exam that's on mastering, so make sure you get to that, and that's gonna be due the Monday of the exam at 2 p.m., right? And that also counts for part of your grade. So the exam kind of has two parts, the pre part, which you'll kind of do on your own. You can use whatever resources you want, and that's through mastering. And then the exam itself, which you'll take through Canvas. All right, I think that's all my announcements. Are there, yes, we will have class on the day of the exam. Wait a minute. No, actually, I take that back. We won't have class the day of the exam. I see a couple questions. Let me take those right now. Sophia?
I don't know if you already answered this, but is there gonna be like Proctorio and stuff?
No.
Okay.
No, I'm just gonna assume that I'm gonna ask you, I'm gonna plead with you to not cheat, to not use any other resources. I'm giving you a lot of resources already, right? You have your periodic table, you have your constants, you have your one page, and you can write down anything you want on that one page, right? So the idea is, so you're not gonna have, and if people try to cheat, they're not gonna have much time to cheat either, because it's gonna be a very, very quickly timed exam. So the point is, you gotta be organized and know your stuff and be able to answer the questions. Okay, so I'm going to ask you to, I'm going to kind of use the honor system here and see how that goes. If that doesn't go well, then we might have to change things up. But I'm hoping that you guys will be honest and play by the rules, and don't sacrifice your integrity for a few points on an exam. It's not worth it. Diana.
Does the pretest have a time limit like the exam?
No time limit on the pretest.
Okay.
It just has to be done before, it's due a week from this coming up Monday at 2 p.m. Allison. Allison Walker.
Hi, so if we do well on the pretest and we, should we feel confident for the exam? Like that's pretty much what's gonna be on the exam?
They're similar, but they're not the same questions. And the exam will tend to also draw a lot on the lectures. I mean, obviously both of them draw on the lectures, but the exam a little more so.
Okay.
Whereas the pretest draws more on the homework, but they both draw on the lectures and the homework. It's just the pre-exam, the pretest, a little more favored towards the homework. The actual exam a little more favored towards the lecture.
Okay.
Good questions. Jane Campbell.
Yeah, I had a question. I was trying to do the pre-lab in the Hayden McNeil website, and it wasn't really working for me. Like, it wasn't letting me into it.
Okay.
And I don't know if anyone else had that problem, but I was just wondering what I should do.
So the lab instructors are really familiar with that. So I would suggest that you send an email to your lab instructor for all lab-related things. Every lab instructor is doing things a little bit differently. So the lab is really their territory. So please contact them. Okay. Any other questions before we get going today? Nayeli.
Yeah, in terms of the periodic table that we're given for the exam, are we able to put our own notes on the periodic table? Or would we have to
I'm gonna say no. I'm gonna say no to that. Only because you have a sheet that you can write up everything you want. I'm going to ask that you keep the periodic table and the equation sheet unmarked, and then put everything you want on one sheet of paper, fit it all in there, and then leave those other two that way. Otherwise, I feel like there's, I sort of open up a can of worms there if I let that happen. Okay. All right. Good question. Thank you. Anything else? Okay, let's see. I had a little technical difficulty here. All right, let's, oh, what happened to my other display here? All right, I'm not gonna worry about it. All right, let's go ahead and get started. I don't see any more questions. I do notice that everyone, I do watch your work on mastering, and most of you are keeping up just fine. There's a few of you that aren't. I've reached out to you via email just to remind you, right, that you have to keep up on that stuff, all right? And if I've reached out to you, I know you've emailed me back, but just remember, once you fall behind by a few assignments, it's really hard to get caught up, okay? And all that stuff is part of your grade, so you have to keep that in mind as well. All right, let's get going. So we are going to, let me just share my screen. And there we go. And hopefully you can all see that. Okay. So we are on chapter 3 of the book, all right? So remember, we kind of progressed up from some elementary things like unit conversion, significant figures, and calculations to stuff like that in chapter 1. In chapter 2, we talked about atoms, right, and elements. And in this chapter, we're going to sort of graduate up to compounds, right, molecules and compounds, all right? And remember that molecules and compounds are when atoms join together, right? So you have the elements on the one hand. Remember our classification of matter. You have elements on the one hand, and then you have compounds on the other, right? And compounds are atoms that have been joined together by chemical bonds, all right? So we're going to start a little bit talking about why do chemical bonds even form. And so remember a while ago, we talked a little bit about how strongly the electron is attracted to the nucleus. And we said that was actually pretty important because, let's see, sorry, I'm having some issues here. Okay. We said that was pretty important because it determines how easily electrons are shared. So why do chemical bonds form, right? Why don't we just have 100 elements? And why do we not just have 100 elements, but rather have all these compounds that exist, right? Why? Because chemical bonds ultimately form. And of course, thank goodness for that, because we're mostly made of compounds, right? So the simplified answer is because they lower the potential energy of the charged particles that compose atoms, right? So we know that atoms are a mixture of these positive and negative particles, right? And in some cases, when they bond together, the reason they do that is because all those charged particles can lower their potential energy. So just like, you know, if I drop something, right? If I drop something, the potential energy goes down, right? Similarly, when atoms join to form a chemical bond, their potential energy generally goes down, okay? I say this is a simplified answer because that's not always the case, all right? We'll learn more about that later, right? The ultimate driving force really for everything that happens is that energy has its tendency to spread out. So chemical bonds really form because energy spreads out, and forming chemical bonds allows energy to spread out. But for now, we can sort of think about it only because we have this nice kind of physical picture of how things go towards lower potential energy, right? So atoms can come together, form chemical bonds, and lower their potential energy. Those charged particles can lower their potential energy, all right? And you can kind of, in a real simplified picture, you can think of something like this. You have two positive charges and a negative charge, let's just say, a real simplified picture. That negative charge, let's say, can be anywhere. Where does that negative charge have the lowest potential energy? Well, it turns out it has the lowest potential energy if it's directly between the two positive charges, right? And that's because it can interact with both positive charges at the shortest possible distance when it's right there, right? So we can think of these electrons, you can think of this negative charge kind of like an electron, right? And notice what it does. It kind of acts like glue, right? Holding those positive charges together, all right? So that's kind of the simple picture of a chemical bond. It's a little more complicated than that, but for us right now, that's fine, all right? We're going to broadly talk about two different kinds of bonds, an ionic bond and a chemical bond, an ionic bond and a covalent bond. And I'm just gonna write those definitions down here. So ionic bond is gonna form between a metal and a non-metal. And a covalent bond is going to form between two nonmetals, two or more nonmetals. Okay. In an ionic bond, the electron is transferred from the metal to the nonmetal. In a covalent bond, the electron is shared between the nonmetals. All right. So here's an example of the formation of an ionic bond right here. So everyone's familiar with sodium chloride, right? Sodium chloride is just salt, right? It's in the ocean, right? It's table salt. We eat it all the time, okay? Sodium chloride is made up of, is a compound because it contains sodium chloride. Sodium is a super reactive metal, right? It's a group 1 metal. We already know from what we know about the periodic table, those group 1 metals are very reactive. So, and we also know, what do we know is characteristic of metals? What do metals tend to do in chemical reactions in terms of their electrons? Do you remember?
Tend to give an electron?
Yeah, they tend to lose electrons, right? So this sodium metal has a strong tendency to lose an electron. Chlorine, on the other hand, is one of the most active nonmetals. And what do you remember about nonmetals in terms of what they do in chemical reactions?
Gain electron.
Gain electrons, exactly right. So this is kind of like a match made in heaven, right? Sodium has its tendency to lose electrons. Chlorine has a tendency to gain it. So sure enough, sodium transfers its electron over to chlorine. Sodium loses an electron, therefore it becomes a positively charged ion, right? Because now it only has 10 electrons instead of 11, right? And then chlorine gains an electron. It becomes a negatively charged ion, all right? Because now it has an extra electron. And now you have an attraction between the positive and negative charges, right? So those are attracted to one another and they form sodium chloride, right? Which notice is a lattice in which you have sodium and chlorine, sodium and chloride ions sort of alternating in position, right? And that's what sodium chloride is, all right? So that's an ionic bond.
Wait, do they have that lattice structure?
Pardon me?
Do they always have like the lattice structure?
Yes, yes. Ionic compounds will always form this kind of lattice where they have alternating positive and negative bonds. Different ionic substances will form different structures, but sodium chloride does. And the sodium chloride structure is responsible for sort of the shape of sodium chloride crystals, right? That you can see when you look at salt, right? Good question. All right, so here's the structure of sodium chloride. You can see it really clearly here. Covalent bonding, you have the electrons shared between the atoms, right? And instead of having sort of a continuous structure like you do here, in a covalently bound structure, you actually have individual molecules, all right? Notice sodium chloride doesn't really have any molecules. It just has alternating sodium chloride ions, right? But in water, when you have covalent bond, anytime you have covalent bonding, like in water, you have individual molecules. And then in the solid, they will have forces between them that hold them in place. But those forces are much weaker than the forces involved in bonding, right? So that's why when, we melt ice, we don't break any chemical bonds, right? We just overcome the forces that hold it in this lattice, in this structure. Does that make sense?
So sorry.
Yeah, go ahead.
So when water freezes, it's cold enough to where the bonds between the water molecules can make it solid?
Correct.
Is that what kind of makes it
freeze? Well, it's the interactions. It's not bonds anymore, all right? It's the interactions between the water molecules themselves. So one water molecule is actually attracted to another. But that interaction is very weak compared to the forces that occur between hydrogen and oxygen to form the bond. In other words, it only takes heating up water to 100 degrees to get it to melt. If you wanted to break chemical bonds in water, you'd have to heat it up to thousands of degrees.
Okay.
That makes sense?
That makes sense. Okay. Thank you.
Yeah, absolutely. Any other questions? Okay, very good. A couple more examples here. Sodium chloride, again, it's because it's such a perfect ionic compound. Another molecular compound would be propane. That's the substance that you use to grill with, right? When you buy propane in a tank like this. Again, notice this is molecular. Carbon, it's carbon and hydrogen, 2 nonmetals, so therefore molecular compounds. It's really important right away in your mind to think about metal and nonmetal. Aha, ionic bond, ionic compound. Non-metal, nonmetal, covalent bond, molecular compound. We call it a molecular compound. Why? Because its individual units are molecules. Okay, and you can see them sort of in this picture. All right, let's do a quick question just to make sure everyone's listening here. All right, go ahead and try this question. All right, 5 more seconds. Put in your answer. Wow, good news. It looks like everyone's recovered from the long weekend. Most of you got the right answer. It's B, covalent. A few of you got A. If you got A, you're not listening very well, or you just got mixed up a little bit. Nitrogen, notice, is a nonmetal. Oxygen is also a nonmetal. What kind of bond forms between nonmetals? Covalent, not ionic. Okay? All right. Very good. Let's move on. Chemical formulas. So a chemical formula is how we represent compounds. All right? We represent compounds with chemical formulas. Let's see. I see a quick question here. Megan, do you have a question?
Sorry. Do you mind saying what you had about molecular compounds? You had said something like they were nonmetals.
Sure. A molecular compound. So ionic compounds are between. Sorry. Let me back up for a minute. If you have a metal and nonmetal, right? You have an ionic bond, and that's an ionic compound. If you have a nonmetal and nonmetal, you have a covalent bond, and that's a molecular compound.
Okay, perfect.
That answer your question?
Yeah.
Sweet. All right, so chemical formula. So chemical formula is how we represent compounds. It indicates at a minimum the elements that are present in the compound and the relative numbers of each. Okay? We have a lot of different types of chemical formulas. So for example, we have an empirical formula. An empirical formula simply indicates a relative number of atoms that are in the compound of each kind of atom. Whereas a molecular formula gives you the absolute number of atoms that are in the molecule, right? And molecular formulas, as their name implies, applies only to molecular compounds, not ionic ones. Structural formula shows how the atoms are connected, and I'll show you some examples of this in just a minute. Ball and stick model shows the actual geometry of the molecule, how it looks in 3 dimensions. And then a space filling model is sort of our best picture of what a molecule might look like if we could actually see it, okay? So here are the 4 representations here are 4 representations of methane, CH4. Methane is the gas that's in your stove. So when you turn on your stove and you light it, right? This is the molecule that's coming out, okay? The methane molecule, CH4, it's very combustible, right? Combines with oxygen, forms CO2 and water, and that's what forms the flame in your stove, all right? So here's the molecular formula, 1 carbon, 4 hydrogens. Here's the structural formula. Notice from looking at this, you really don't know how the atoms are bonded together, right? You might say, oh, well, wait a minute. Are the atoms bonded together like this, for example, right? Or are they bonded together like in a circle, right? You don't know, right? You don't know just from looking at this how the atoms are bonded together. So the structural formula tells you that information. It shows you, the carbon is connected to the hydrogens, and none of the hydrogens are connected to each other, okay? Does that make sense? Nod your head, does that make sense? Perfect, thank you.
Why don't you go over some more examples, man? Fucking shit.
What's that, Raphael?
Oh, I'm sorry about that. I didn't know my mic was on.
Okay, I'll go through some more examples, don't worry. Here's the ball and stick model, right? This is the carbon atom. These are the hydrogen atoms. Notice that here in the structural formula, the molecule looks kind of flat, right? But the molecule really isn't flat. In 3 dimensions, notice it has this geometry, right? So the ball and stick model conveys that. And then finally, the space filling model, we know that these sticks really don't exist, right? There are no such things as these little sticks, right? We're using them to represent bonds, but bonds are really just interactions between atoms, right? Where the atoms are attracted to one another. So this is kind of our best picture, right? Of, oh, wow, if we could see molecules, what would they look like? Well, this would be our best idea of what they look like, all right? Here's some more examples. Here is, we'll look at benzene here. The molecular formula is C6H6. 6 carbon atoms, 6 hydrogen atoms, all right? The empirical formula, remember, just gives the simplest ratio of the atoms, right? So the empirical formula is just CH. All right, here's the structural formula. In this case, the carbons are all bound together in this ring structure and the hydrogens are bound to that, all right? And you might say, well, why do we care? Well, of course, what do we know about the main story of chemistry, right? The main story of chemistry is that structure is everything, right? The structure of a molecule determines the properties of the thing that the molecule composes, right? So we really care a lot about structure, and that's why we're taking all this time and energy to sort of be able to show what that structure is on paper, right? Here's the ball and stick model. Here's a space filling model for benzene. Acetylene, this is the gas that's used in an acetylene torch for burning, right? It has the formula C2H2, 2 carbon atoms, 2 hydrogen atoms. The empirical formula would be the lowest common, would be the simplest ratio of carbon to hydrogen, which you can see here is 1 to 1. So that's the empirical formula. Here's the structural formula. Notice that it has these triple lines. That's something called a triple bond. Here you have double lines. That's a double bond. Here you have 1 line. That's a single bond. Don't worry about what any of that means right now. We'll talk more about those later when we begin to understand chemical bonding a little bit better, okay? Space filling model and so on. Here's glucose, right? Glucose is a type of sugar. It courses through our veins. It's kind of the energy currency that we all run on, right? It has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Its empirical formula is CH2O. That's why sometimes these kinds of molecules are called carbohydrates, because carbon and water, carbohydrates, but they really don't have any water in them. They just have that formula, okay? Here's the structural formula, space filling, and so on. Here's ammonia. Notice that in some cases, the molecular formula and the empirical formula can be exactly the same, right? For NH3, the simplest ratio is NH3, and that's also the molecular formula. Here's the structural formula, shows that the nitrogen's in the middle, bounded to the hydrogens, and then space filling, ball and stick and space filling. Does that make sense? Different kinds of formulas.
Sorry.
Do you have a question?
I was just wondering, isn't there another way to show it called like the Lewis dot model, which shows like the electrons? Or?
So the Lewis dot model is a theory for chemical bonding. All right.
Okay.
So it's a chemical, and you're right. We'll see later that we can draw structures called Lewis structures for compounds, but that's the application of a theory that helps us understand, you know, why is water H2O and not H3O, for example? The Lewis model can tell us that, okay?
Got it.
Right now, we're just looking at formulas, but we'll get to the Lewis model later in the semester.
Okay.
Good question. Any other questions? Okay.
Sorry. When do we use the empirical formula and the molecular formula?
You know what? It just depends. I want you to know the difference between them, right? And be able to use one when we talk about empirical formula and use the other when we talk about molecular formula. It just depends on what you're doing. Okay? All right. So another question. Go ahead and answer this one.
Oh.
All right, 10 more seconds. 10 more seconds. Answer, please. Okay, and the correct answer is C. And again, thank you for responding and thank you for paying attention. Nearly everybody got that correct. A few of you answered D. Let's see, what kind of formula is D? Who knows?
It's a chemical formula.
Okay, so the chemical formula is the broad term that applies to all kinds. This is a specific kind of chemical formula. Which one is it?
Molecular.
Correct. This is the molecular formula, right? It just shows the number of each type of atom in the molecule, right? But it doesn't show the structure, right? This shows the structure. So that's why this is the structural formula. Does that make sense?
Yes.
Yes.
Very good. Okay, let's move on. Here's another question. Let's try this one. Go ahead. Okay, 10 more seconds. Okay, I'm going to stop it there, show the results. So here, the correct answer was B, and most of you got it. A few of you got held up here with A. So why is A not the empirical formula for this compound? Who can tell me?
1-to-2 ratio.
Yeah, see, there's 3 carbon atoms and 6 hydrogen atoms, right? So the simplest ratio is 1-to-2, right? If you divide these both by 3, you get C1H2. So that's why it's B, right? CH is not the empirical formula for this compound, right? Because it doesn't have the right ratio of carbon to hydrogen. Does that make sense? Skylar, do you have a question?
Yeah, so are we going to need to know how to get from the empirical form to the molecular form of a compound?
Well, if you just have the empirical formula and that's all you have, you can't really figure out the molecular formula. You can go the other way. So in other words, you can go from the molecular formula to the empirical formula, right? But there's a lot of compounds. There's a lot of possible molecular formulas for this empirical formula, right? Because I can have CH2 could be one of them. C2H4 would be the next one. C3H6 would be the next one. C4H8, right? So without more information, if someone just said, hey, the empirical formula is CH2, what's the molecular formula? I couldn't answer that question without more information, all right? we will see that with more information, we can answer that question, and we'll be doing that a little bit later, okay? Good question. Any other questions? Okay. Again, thanks for answering and for paying attention here. I think we're in good shape. All right, let's look real quick at a particulate view of elements and compounds, all right? So up here you have all pure substances. Remember, a couple of weeks ago we looked at matter, and we said matter can be a pure substance or it can be a mixture, right? So if it's a pure substance, we learned that it can be an element or it can be a compound, all right? Now for these two categories, we have some subcategories, right? For elements, elements could be atomic or they could be molecular, all right? In an atomic element, atoms are the fundamental units that make up atomic elements, all right? If the element is molecular, molecules are actually the fundamental unit that make up that element, all right? But there are molecules in which two or more of that atom are joined together, okay? And we'll see some, and I'll show you which elements form molecular compounds in just one moment, okay? Compounds, on the other hand, can be molecular, like we just talked about, right? In which case you have nonmetals and nonmetals bonded together and they form distinct molecules, right? Or they could be ionic, metal and nonmetal. Notice no distinct molecules, all right? We call the simplest ratio of ions here the formula unit, all right? So formula unit for an ionic compound is kind of like the molecule for a molecular compound, all right? But it's really just the empirical formula, all right, for that particular compound. All right, so what elements are molecular? What elements fall into this category? Well, here are all the elements, right? The vast majority of them fall into this category, okay? The vast majority of elements are atomic. The molecular elements are the ones that I've highlighted here, all right? Hydrogen, nitrogen, oxygen, and then all the halogens, all right? These all exist as diatomic molecules, right? So kind of like this, O2 exists as two oxygen molecules bound together, right? So you see oxygen here. All the rest of these in yellow are very much the same thing. Two of those atoms bond together to form a molecule, all right? Then they have these three elements that exist as polyatomic molecules. In other words, more than two bound together. We're not going to worry about these too much. I do want you to know these for sure. So hydrogen, nitrogen, oxygen, and then the halogens all exist as diatomic molecules. So make sure you're familiar with that. So if you have a sample of chlorine, you don't really have any chlorine atoms, right? You just have chlorine molecules. I see a couple of questions. Javier.
Yes. I was just wondering why is that those specific elements exist as a compound?
Yeah, so the answer to that question is the same as the answer to why molecules form or why compounds form. So it turns out that they can lower their potential energy by bonding together. So if you have those atoms, let's see, Emmanuel, can you mute yourself?
Yeah, I was just gonna say a good way to remember that is H naught and then down to I.
Oh, perfect. H naught and then down to I.
Down to I.
Okay, yeah, very good. Thank you.
I don't know if that helps anybody out, but that was how I remembered it.
Yeah, good job. Thanks, Emmanuel.
Yeah.
Other questions? Okay. All right, so here's a quick question for you. Go ahead and answer this. Okay, 10 more seconds. All right, and the right answer is B, right? And again, most of you got that. Very, very good. Let's see. A few of you put A, not very many, but just a few said atomic element. You know it's not an atomic element. Why? Because this picture shows that it's broken up into molecules. Remember, an atomic element would look like this, right? Where the individual units are actually atoms, okay? So it's not an atomic element. And then a few of you put C, which is a molecular compound. The reason you know it's not a compound is because compounds have to be composed of different types of atoms, right? But because this is composed of only one type of atom, notice both of the spheres are the same color, right? That tells you that this is a molecular element. All right, awesome. Thank you. Let's move on.
Wait, question, sorry.
Question, yeah. Hey Yoon, is that Hey Yoon have their hand up? Yep.
Yeah, so I just wanted to double check. So if it's molecular element, I think, like no, so if it's a molecular compound, like compound is like, it has to be made up of like different atoms, whereas if it's like molecular element, it's just only consists of like that one.
Correct. So remember, for all pure substances, again, I'm referring back to the classification of matter that we did a couple weeks ago. And you had in that diagram, you know, we had pure substances on one side and mixtures on the other, right? So now we're just focusing on pure substances. Pure substances themselves can be two types, elements or compounds, right? So elements, remember, if it's an element, it has to be on the periodic table, right? So here are all the elements that exist, right? There's only 100, well, a lot of these are synthetic, right? So, but 118 of them, right? On the other hand, compounds, there's hundreds of thousands, millions and millions of different compounds, right? There's a lot of different compounds because they are made by putting these elements together, okay? So that's elements versus compounds. Within compounds, they can be molecular ionic. Within elements, they can either be atomic or molecular, and that depends on their individual units. That makes sense?
Yes, yes. Thank you.
Yeah, you're welcome. Any other questions? Okay, now we have a couple of topics for which you already watched a video, right? The pre-lecture video today was on nomenclature, right? On naming compounds. So I'll go through the rule, I'll go through the procedure very, very quickly, and then we'll do some examples, all right? But hopefully you already saw the procedure and you already did all that before coming to lecture today or before watching this recorded lecture if you're watching the recorded lecture, all right? So before we get started here, though, on nomenclature, the first thing you got to be able to figure out is, do we have an ionic compound or a molecular compound, right? So really quickly, which of these compounds is ionic? Go ahead and answer that question. If you can't get this question correctly, then you can't name the compound, because the first thing you got to do is figure out, is this ionic or is this molecular? Okay, looking pretty good. Five more seconds. Which compound is ionic? Okay, the right answer is D. And again, the vast majority of you got that. A few of you were scattered throughout other places. Remember, what's characteristic of an ionic compound?
Metal and non-metal.
Metal and non-metal, right? So here you have your periodic table, right? That's why I have it here. So the only one that falls into that category in which you have a metal, which is this area, and a non-metal, which are found up here, is MgBr2, right? Here's Mg, sorry, right? And here's Br, right? So notice that's metal and non-metal. All the rest of these are non-metal, non-metal, right? So what kind of compounds are these other ones?
Molecular.
Molecular, correct. Exactly right. Very, very good. Okay, so we're on the right track. So we need to answer that question before we name it, right? Now we're going to assume that we're dealing with only ionic compounds. How do we name ionic compounds? Well, first of all, we got to look at the metal, and we got to decide, is it one of two types? Is it the type that always forms the same charge? These are the metals that always form the same charge. Okay, actually there's a couple others, but these are the main ones, all right? And for those kinds of metals, you don't have to mention the charge in the name. Why? Why do you think?
Because it doesn't change.
Because it doesn't change. It's always the same, right? If you have calcium, it's always calcium 2+, right? If you have aluminum, it's always aluminum 3+, right? Javier, question.
Yeah, so we were talking about ionic bonds and covalent bonds, right?
Yes.
But what can two metals bond?
Yes, and that's a metallic bonding, which we're not really going to deal with right now. Sort of a more advanced topic. Yeah, thanks for asking though. Okay, so the first thing I want you to be able to do is figure out what the right formula is for the compound, right? For ionic compounds. So for ionic compounds in which you have any of these metals here that always have the same charge, you can easily figure out the formula if you know what the two elements in the compound are, right? So for example, if I have potassium and nitrogen, right? I have potassium and nitrogen, right? That's an ionic compound, right? Metal and non-metal. What's the charge of potassium?
1+.
Yep, exactly correct. And then what's the charge on nitrogen?
3-.
3-, right? So 3-. What do we know about ionic compounds? They have to be charge neutral, right? They can't, the formula has to be such that it's charge neutral. So how can I form a charge neutral formula between these two ions?
3 potassium atoms.
Exactly right. So that would be K3N, right? Notice that that's now +3 -3, right? These three together form a +3 charge, and then the nitrogen is 3-, so this is charge neutral. All right, let's go to calcium and bromine. What charge does calcium always form? Here's calcium on the periodic table.
2+.
2+.
2+, exactly right. And then what about bromine?
1-.
1-, right? Bromine's over there at 1-, so bromine minus. So what has to be the formula for this compound?
CaBr2.
Yes, exactly right. CaBr2, right? Okay, how about aluminum and sulfur? What's the charge of aluminum?
3+.
3+. And then what's the charge of sulfur?
2-.
2-. So how are we going to form a neutral compound between these two ions?
2 aluminum atoms and 3 sulfur.
Exactly right. Al2S3, right? Why? Because these two together, right, are 6+. 2 times 3+ makes 6+. And these three together, right, make 6-, right? Because 3 times 2- is 6-, yeah? So again, the formula for compounds has always got to be charge neutral, right? So you can figure out formulas for compounds containing these elements. Since they always form the same charge, you can always figure out their formula just from knowing what the elements are. Does that make sense?
Yeah.
All right, go ahead and try this yourself now. Okay, 5 more seconds. All right, the right answer was B, and look at that. Almost everybody got that. Very, very good. A few of you put C, but really quick, right? What's the charge of rubidium? Notice rubidium is here in group 1, so it has a charge of +1, right? Over here you go to oxygen. Oxygen has a charge of 2-. How can you make a neutral compound between these two? You need 2 of the rubidiums, right? Because that'll give you 2+ to balance out the 2-, right? So it's RB2O, right? If you had RbO2, right? This would be 4- and this would be plus, so that would not be charge neutral. Okay, does that make sense? Let's see. Jess, do you have a question?
Yeah, so I was just wondering, because earlier you had said that oxygen existed as a diatomic molecule.
Correct.
So even though it's technically 2 oxygen atoms, it doesn't show up as O2?
Oh, very good question. So remember, when it forms a compound, it does totally different things than when it's an element, right? So as an element, it's O2, but in compounds, there could be 1 oxygen atom, there could be 2, there could be 3, there could be 4, there could be 5. It just depends on the compound.
Oh, okay. So it's just O2 when it's unbonded.
Correct. Well, when it's
right.
Not in a compound.
Yeah. Okay.
Still
Cool.
bonded. Yeah. Good.
Thank you.
Good. All right. Any other questions?
I have a question. In my periodic table here, I have written the charges, but how do we know the charges if we don't have a periodic table like mine?
You have to remember that. So you have to remember that this is 1+, 2+, right?
Uh-huh.
Aluminum is 3+, and then you go over here, it's 2-, 1-. All right, so it's by column.
Okay.
Basically, you need to memorize this chart.
I see. Okay.
And this is in your book, okay?
Okay. Thank you.
Okay. Yeah. You're welcome.
Also, I was gonna ask. Which ones? Because I know like a couple more below aluminum are also 3+ charge. Do you want us to just memorize that chart right there? Do you want to?
These are the ones that you need to memorize to be able to write formulas for. Okay.
Okay. Perfect.
The other chart is for nomenclature, and we'll get to that in just a second. Okay, Emmanuel.
Okay. Thank you.
Okay.
What about row 4A? Doesn't that have a 4+ charge?
Sorry, Raphael, say that again.
What about row 4A? Doesn't that have a 4+?
Nope.
All right, thank you.
Yeah. All right, so naming ionic compounds, right? Now we want to be able to name them. Again, remember metal and non-metal. Now we got to decide, okay, does the metal form only one type of ion or does it form more than one type of ion? Okay. Most main group metals and these 3 down here form one type of ion. Most transition metals and lead and tin form more than one type of ion. This is very well spelled out in the video that you watched today, okay? If you haven't watched that video yet, make sure you go back and watch it right after the lecture because it'll be very important for you to be able to name these compounds, okay? These metals shown here always have the same charge, all right? So notice the ones we've already seen plus the 3 more scandium, silver, and zinc, right? Because these are transition metals, right? So transition metals usually can have different charges in different compounds, but these 3 are exceptions, all right? And so the way we name these is we put the name of the metal, right? And then the base name of the nonmetal plus the ending "-ide". So let's practice, right? How would we name KCl?
Potassium chloride.
Correct. It's just the name of the metal, potassium, the base name of the nonmetal, chlor, because it's chlorine, plus the ending "-ide", so it's potassium chloride. How do we name CaO?
Calcium oxide.
Correct. Calcium oxide. Name of the metal, calcium. Base name of the nonmetal, ox, with the ending "-ide", so calcium oxide. how would we name K3N?
Potassium nitride.
Exactly right. Potassium nitride. And then how would we name Al2S3?
Aluminum sulfide.
Aluminum sulfide. Notice that none of these names have di, tri, or anything like that in them, right? We know that aluminum sulfide has to have that formula. Why? Because aluminum is always 3 plus and sulfur is always 2 minus. So this is the only formula that can exist between aluminum and sulfur. Does that make sense?
Yes.
Okay, very good. Now, what if the metal forms more than one type of ion? So the metals that form more than one type of ion are the transition metals plus these 2 main group metals. Okay, so it's all the transition metals except for the exceptions that we just talked about. And then these 2, which are also exceptions. These form more than one type of ion. All right, and when you have those, any of these metals, you have to indicate the charge. All right, so for example, chromium can exist as 2 plus or 3 plus. Iron can exist as 2 plus or 3 plus. We note the difference by calling this one iron 2 and we call this one iron 3. This is an older system that you might see. We're not going to use that in this class. Okay, we're just going to use the numbers, right? So chromium 2, chromium 3, and so on. All right. So how do we name these compounds, right? We put the name of the metal and then the charge of the metal and the base name of the nonmetal plus the ND9. All right, so let's start with this one, CrBr3. How would we name that? One more time.
Chromium 3.
Yes.
Bromide.
Chromium 3 in Roman numerals and then bromide. There is no space here and there's a space there. Okay, is the correct way to write it. How did you know it was chromium 3? Well, you look here and you know the Br is -1 and there's 3 of them, right? So in order for this to be charge neutral, what does chromium have to be?
3 plus.
3 plus, right? Does that make sense? All right, let's try CuO.
It's copper 2 oxide.
Copper 2 oxide is correct. How do you know? First of all, copper is one of those elements that doesn't always have the same charge. Remember, those elements are the transition metals plus these 2, okay? And copper is a transition metal, all right? So it has a charge that can vary. How do we know it's 2? Well, we know oxygen is 2 minus, right? So to have a neutral formula, copper is going to have to be what? 2 plus, right? So it's copper 2 oxide. All right, what about CO3N2? Anybody want to take a guess at that one?
Would that be cobalt 3 nitride?
Cobalt. Okay, let's
Wouldn't it be 2?
Cobalt 2 nitride is correct. Cobalt 2 nitride. How do we know that? Let's figure this out. What is nitrogen normally? Let's go back to this.
3 minus.
Go back to this table. So far back. Sorry. What is nitrogen?
3 minus.
3 minus, right? And we have 2 of them, so that's 6 minus. So we know that the 3 cobalts together must be what?
6.
6 plus, right? The cobalts together must be 6 plus. Sorry, let me just get back to where we were. So there's 2 of them, so each one is going to be what? Sorry, there's 3 of them, so each one's going to be what?
2.
2 plus, right? Each one's going to be 2 plus. All right, so the correct name is cobalt 2 nitride. All right, what about this last one? PbCl4, how would we name that?
Lead 2 chloride.
Okay, you're close.
Lead 4.
It has to be lead 4, right? Because what's the charge on the lead ion? since you have 4 chlorines and the chlorines are always -1, in order to have a neutral compound, lead must be what?
Plus
Plus 4.
4 plus, right? So this would be lead 4 chloride.
Oh.
Okay, does that make sense?
Yes.
All right, here's one for you to try. You guys ready? Oh, wait a minute. Yeah, let's have you try. Let's go ahead and have you try this one. Oh, shoot. Okay. Let me point out, I see the issue here. Let me point out where strontium is. Okay. So strontium is here, right? What kind of metal is strontium? Does it always have the same charge or does it have different charges?
Same charge.
Same.
Always has the same charge, right? Always has the same charge. So keep that in mind. Remember, metals here, aluminum, and then a couple of other exceptions always form ions with the same charge. So when you have a metal that always forms an ion with the same charge, do you need the Roman numeral?
No.
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 You do not. Okay, 5 more seconds. Okay, so the right answer is A. And a lot of you got that, but a lot of you didn't. A lot of you put in the Roman numeral. The Roman numeral doesn't belong here, right? Why? Because of the metal, right? The metal is strontium. Look where strontium is. It's a main group element. It's in row 2. It always has the charge 2+. So you do not have to indicate the charge of the Roman numeral. Does that make sense?
Yes.
Okay, let's try another one. Try that one. Iron is right here, by the way. Fe. It's one of those that is, its symbol, it's based on its Latin name, which is why it's Fe and not IR or something.
Wouldn't IR be iridium?
Yeah, exactly. All right, 5 more seconds. Okay, the right answer is C. And this time, most of you got that. Very, very good. A few of you put B, iron trichloride. Remember, in ionic compounds, you never have di-tri, no prefixes, right? This is an ionic compound. That's why the very first question I asked you was, what kind of compound do you have? That's the first question you have to answer, right? Metal, non-metal, aha, that's ionic, right? So no prefixes. Javier, I see your hand up. Did you have a question?
Yeah, I was just wondering, it's always when naming compounds that the metal comes before the non-metal?
Correct. Yep. In all ionic compounds, you always list the metal first.
Okay.
When you write the formula and when you write the name.
And what about the covalent?
Yes. In that case, then what you do is you put the element that's most metal-like first. So, for example, if you're writing the formula for the compound between carbon and oxygen, since carbon is further to the left of the periodic table, we'd write that one first. Okay.
Thank you.
Yeah.
I have a question.
Yeah.
So how do you know the charge of the iron?
Oh, right. Good question. I figured it out from the formula, right? So the formula is FeCl3.
Mm-hmm.
I know that I have 3 chlorines, and what's the charge of chloride?
3?
No. The chloride ion is -1.
Oh, no, sorry, -1.
But there are 3 of them, so it's -3. So in order to form a neutral compound, what must iron be?
Oh, so that's why that has to be 3.
Exactly. That's how you figure it out. Okay? Good question. Let's see. Let's try writing a formula, right, based on this information. Right, so if I have the copper-2 ion with a nitride ion, what must that formula be? I have copper with a 2+ charge. I have nitrogen. What's the charge on the nitride on nitrogen?
3
The CuN2.
3-, right? So how am I going to form a neutral compound between these two?
Cu3N2.
Yep, Cu3N2. All right. What about iron 2 with a bromide ion? What would that formula be?
Would it be iron 3?
Sorry, I'm looking for the formula now. I know that I have Fe2+, so that's iron 2, and Br-. That would form a compound with what formula?
FeBr2.
FeBr2, that is correct. Okay, see how that's charge neutral. Okay. All right. Let's talk a little bit about polyatomic. Actually, let's see. Do we have a question? Nope. Okay. Polyatomic ions. A polyatomic ion is a group of nonmetals with a charge. Okay, it's a group of nonmetals with a charge. So for example, here's something we've been using a lot lately, bleach, right? Because it kills coronavirus. So we've been using bleach to clean things and clean surfaces and things like that. The active ingredient in bleach is sodium hypochlorite. Sodium is a metal. Hypochlorite is a polyatomic ion. All right, it's an ion made of 2 nonmetals. In the case of hypochlorite, it's chlorine and oxygen. Here's the table, 3.4 in your book. I would like you to memorize this table. Okay, this table you need to know. All right, you need to know. It's going to be very handy for you as you do your work to be able to do it quickly if you're very, very familiar with this table. Of course, you can write it on your cheat sheet if you want, because you can write whatever you want on your cheat sheet. But if you have to look it up every time, it's going to take a long time. So it'd be really helpful to know this table. Know the names, the formulas, and the charges. Okay, because these are all the common polyatomic ions. Here's hypochlorite right here, the one we just talked about, ClO-. Okay. Notice some subtle differences here. Nitrate is NO3-, but nitrite is NO2-. All right, so the name goes with the ion, and there are some subtle differences between these that'll be very, very helpful for you to know. Okay. So when you have a polyatomic ion like this in an ionic compound, you just use the name of the polyatomic ion in place of whatever is there, right? So for example, if I was to name NH4Cl, right, I would go back and I'd say, aha, NH4, what's that? Oh, that's ammonium, right? So I would just use the name ammonium. right? And then the anion is chlorine, so it'd be chloride. Okay. Let's try naming this one. What would we name that one? The name of C2H3O22, right? So we name it calcium. Again, all of these compounds that contain these polyatomic ions are ionic compounds, all right? So we name them just like we would ionic compounds. The only difference is when you have the polyatomic ion, just use the name of the polyatomic ion, all right? Otherwise, the rules are exactly the same. So this is calcium, right? And then what's this polyatomic ion? Go back to our table. Aha, it's acetate, right? C2H3O2-, so we name calcium acetate. Do we need a Roman numeral here to specify the charge on calcium?
No.
No, right? Because it always has a charge of 2+, right? Calcium is right here. It's in this column, right? Okay, what about the last one here? CuNO32. How do we name that?
Copper nitrate.
CuNO32. Okay, so I heard copper nitrate, but you're close there, but copper is what kind of metal? Look where copper is. It's right here on the periodic table. Does it always form the same charge, or does it form different charges in its compounds?
Different
charges.
Different charges, so we need to use the Roman numeral, right? So how do we figure that out? Well, we know NO3 is -1. It's the nitrate ion, right? Right here, okay? It's a nitrate ion. There's 2 of them. So what's the charge on the copper?
+2.
+2. So what's the name of this thing?
Copper 2.
Copper 2 nitrate. Does that make sense?
I have a question actually about the first one.
Yeah.
So let's say, for example, there were like 2 chlorine atoms. Would you have to make that into like dichloride, or does that apply?
No, ionic compounds never have ditri instead in them.
Okay.
Only molecular compounds. Okay. Okay, let's have you try this one.
Is the ammonium chloride considered ionic?
It is. You have to recognize it's one of the few compounds that's actually all. It's one of the few ionic compounds that's all non-metals.
Okay.
You just have to basically have to learn that NH4+ is a polyatomic ion.
Okay.
I think it's the only one actually. Okay, 5 more seconds. Okay, the right answer is C. And most of you got that, but a few of you were thrown off, right? Why is it C? What's potassium? Group 1 metal, so what's its charge? +1, right? What's carbonate? Carbonate is a polyatomic ion. It has a charge of 2-. In order to get a neutral formula, do you need 2 of these or 2 of these? 2 potassiums or 2 carbonates?
Potassiums.
2 potassiums, right? So it's K2CO3. All right, molecular compounds. So remember, molecular compounds are non-metals and non-metals, okay? How do we name those? Those are a little bit easier. Basically, all you do is you have some prefix which tells you the number of atoms of the first element, and then the name of the first element, and then another prefix which tells you the number of atoms of the second element, and then the second element plus I, the base name of the second element plus I, right? So if you have N2O4, right? It's simple. Dinitrogen tetroxide. 2 nitrogens, 4 oxygens. Dinitrogen tetroxide. Here are the prefixes. This is another table that you have to memorize, right? You have to know what these prefixes are. Mono, di, tri, tetra, penta, hexa, hepta, and so on. Okay? Let's practice. How do we name N2O4?
Dinitrogen. Tetroxide.
Dinitrogen tetroxide. Very good. How about PCl5?
Phosphorus.
Oh, I forgot to mention one thing. Mono is not used on the first element. So if the first element is just 1, you just drop the mono. All right? So you might think monophosphorus, but then just drop the mono. So what would it be?
Phosphorus pentachloride.
Exactly right. Phosphorus pentachloride. All right. What about this one?
Diiodide heptafluoride.
Not hepta. Oh yeah, hepta. Good job. Good job. Hepta. Diiodine heptafluoride. Okay. All right. Try this one yourself. Okay, 5 more seconds. Okay, wow, nice job. Virtually everybody got that. It'd be phosphorus pentafluoride. All right, good job. All right, real quick, I know we're almost out of time, but I do want to mention a little bit about acids, because acids are another type of compound that is made of a metal and another, sorry, of a non-metal and non-metal. You can recognize acids because they're always going to be written with a hydrogen first, okay? So some examples of acids are things like hydrochloric acid or nitric acid. Acids have some characteristic properties. They have sour taste, right? So lemons and limes get their sour taste from primarily citric acid, which is present in these, right? And they will dissolve metals as well. But how do we name them? Well, it turns out there's 2 types of acids. There's binary acids, those that only have hydrogen and one other element. And then there are oxyacids, those contain hydrogen, oxygen, and some other element. Okay, and those are named separately. All right? Really quick, binary acids are super simple to name. You just put the name of, it's just called hydro for the H, and the base name of the nonmetal, and then the ic, and then acid. So how would I name HCl?
Hydrochloric acid.
Correct. Hydrochloric acid. And HBr?
Hydrobromic acid.
Hydrobromic acid. Exactly correct. Okay? Those are binary acids. I'm going to skip the question because we're almost out of time here. Oxyacids, they contain oxygen as well, right? So they don't just have 2 elements, they have 3 elements, typically hydrogen, whatever the other element is, and then oxygen. And these can be divided into 2 types. And the types depend on the name of the polyatomic ion, right? So this polyatomic ion is nitrate, right? So notice it ends in 8. This polyatomic ion, sorry, that should be subscript, is nitrite, all right? So if it ends with an 8, you name it with the ending ic. If it ends with an I, you end it with an ending us. Here's an easy way to remember this. Ic, I, 8, an acid. Ick, I ate an acid, right? So if the polyatomic ion ends in 8, then you know that the naming goes with ick, right? Otherwise it goes with us. So how do we name this? HNO3 is nitric acid, right? Why? Because NO3 minus is nitrate, okay? How do we name H2SO4? That would be sulfuric acid, right? Because this is sulfate, okay? On the other hand, NO2 is nitrite, so then that becomes nitrous acid, right? And H2SO3, SO3 is nitrite, so that becomes sulfurous acid, okay? So these endings depend on the ion, right? Okay, I'm really sorry. I went over there. I apologize for that. If you guys want to stick around, I can do some more examples of these because I rushed that a little quickly. There's a really nice table in your book that summarizes all this, right? I encourage you to look at that table, right? It tells you, well, do you have an ionic compound, molecular, or an acid? And then you kind of branch down and you can name things according to what you have, all right? And you have plenty of practice doing nomenclature because you will be doing that this week on your problem set, right? Again, if you haven't watched the video that was the pre-lecture video, make sure you go back and watch that. Or if you're having trouble with this, make sure you go watch it again. Okay, we're over time, so I'm gonna call class ending here. Of course, I will stick around and answer any questions you might have. So let me stop sharing my screen, and I'm going to stop the recording.